like it's going to be
It's like the building code is called.
like I didn't really necessarily.
Okay, did everyone see the announcement about labs?
Yeah.
Okay, so no labs this week because the chancellor is coming tomorrow and every professor is supposed to be at that. And his talk is right over the top of one of our labs, so we can't have any labs. So I don't know if you're still having, I don't know how many of you are still having labs tomorrow, but do know that there is a meeting with the chancellor that we were told by our dean that professors are supposed to be at, so.
What times does that run?
Starts at 1 o'clock, and from that, they don't give an end time because, well, look, once the chancellor is like the top guy in the whole system. It's really his prerogative when it ends. Usually he talks for about an hour, but again, it's his prerogative. Okay. So what I wanted to,
Maybe you should just go see it.
so I noticed last time there were a few faces that were a little confused about displacement vectors. So I kind of wanted to start with calculating some of those so you can get an idea of what we're talking about.
Google.
Not what you're supposed to be showing.
Yep. Right, like.
Not crazy.
But that also sucks because we also have immunology test right now. Which would make our immunology test.
I'm saying.
And then if you could say.
It's fine. Y'all gotta really.
I can have
Just say 20 points vector.
we can have a lot.
Just go straight to the question. 8 weeks.
No, not the.
Yeah.
Yeah.
I know, I started after 3 and I was like, but I mean, like, that's like 5.
I just need to know if it's a 5.
Okay, so let's see if we can actually do this. I'm not in what you would call the greatest mood at the moment. Okay, so we're going to look at displacement vectors. So what I'm going to do is I'm just going to start by drawing some vectors in here. So I put some new ones in.
Okay. Thank you.
These were kind of like last minute slides because, again, I want to make people more confused by this process.
Wait, well does this week's assignment cover displacement vectors?
No, it's not on the assignment for this week. Everything on the assignment due on Friday should be from calculus. Okay, so what we're going to have here. These are our position vectors. Okay. Now, we need some directions here. So let's say we have an angle there, one there, and one there. So we're gonna have angle theta, phi. What's that little letter? That's a delta. So delta is that, sigma's that. So it's kind of like a sigma on its end. Okay, so think about displacement vectors. We have one that goes from 1 to 2. One that's going to go from 2 to 3. And so what these are going to be is your delta R1 and delta R2. That's just your displacement 1 and your displacement 2. Okay. But you know we're going to have, because remember, total displacement is a vector addition. So we're going to end up needing to get components for all of these. Okay, so y, x, 2y, 2x, 3x, 3y. So, as of right now, to start analyzing this is all we're going to need. In a little bit, we'll draw these displacement vectors. We're going to move both of those delta r's to the origin, so we can kind of see which way the total displacement would point. So, here's some magnitudes. And we have some angles. So theta, phi, and delta. And then we're just going to kind of have to start in doing the components for each individual position vector. So for R1, we have R1 cosine of theta, R1y, so we put in our numbers. So R1 is going to be 3.0. So first off, you notice how I start with the equation for the component. Always make sure you're doing that. Y is going to be 3.0. Minus 75. Okay, so that's going to give us 0.776 over here. 2.90 over here. And then we think about R1, it's in quadrant 2. So it's going to have to be a negative 0.776 pi hat. And a positive 2.90 j hat. Y is positive, X is negative. So then we can write this one. So there's our vector. There is our position vector 1 in vector component form. Now we're going to have to do this for the next two vectors so that we can end up getting the displacements and then the total displacement. Because we're going to get 3 vectors, then we're going to do 2 vector subtractions to get the displacement vectors. Then we're going to do a vector addition, adding together the 2 displacement vectors. So it's just step by step. R2x, that is going to be R2 cosine of phi, R2y, R2 sine of phi. All right, magnitude of R2, 4.5. Cosine and the angle for R2. Give us 9 and 2.25. The R2 is in the first quadrant, so these are both going to stay positive. And so now we have R2. Two of the vectors we need. Now let's get the third position vector. Cosine of delta, R3y, R3 sine of delta, and we're going to end up with 1.29. This one is going to be 1.3. R3 is in the fourth quadrant. It's going to be a positive x and a negative y. Okay. So let's go ahead and write this one. All righty. So we have our three position vectors. Now, we need to calculate our two displacement vectors, which is going to be vector subtractions. So subtraction between 1 and 2, subtraction between 2 and 3. Okay, so it's going to be R2 minus R1. So what that's going to look like, R2x minus R1x, your I hat, R2y minus R1y, that's your j hat. Now, one thing that I've been seeing, that I've seen a couple of times, not happening a lot, but I've seen people solving for the x and y components, and then for net force, they do x plus y plus x plus y. You only add together x's, you only add together y's. You're not adding all of these up. And so you notice that your vector subtraction sets up the same way as addition. It's just you're putting a minus sign in instead of a plus. So what are those numbers going to be? R2x is 3.90. R1x is a negative. So it's going to be the negative of a negative 0.776, so it's going to be plus. R2y, 2.25, and R1y, 2.90. When you add all these together, your first displacement vector, 4.68 minus 0.65. If you go back up and look at the direction of delta R1, you can see that if you placed an XY axis on the end of delta R1, it's pointing into the fourth quadrant. So these components make sense. Now let's look at delta R2. That is going to be position 3 minus position 2. So same kind of setup. We're just subtracting position 3 where the vectors R3 and R2. And does it make sense to you why I did 2 minus 1 and 3 minus 2?
Final minus initial.
Yeah, so remember, you don't want to do it the other way because in science, your delta is always a final minus initial. Okay, so R3x is 1.29, R2x 2.90. So that's our I hat direction. And then R3y, negative 1.53, minus R2y, which is 2.25. When we add these up, our delta R2, 2.61, I hat, minus 3.78, j hat. And again, if you look at the delta R2 and you look at the way it's pointed, you can see that if you put XY axes on the tail of delta R2, it was pointing to the third quadrant. So you do need 2 negative components. Okay, now you found your 2 displacement vectors. Now you need to find the total displacement. Okay, so what does that look like? So remember, this is going to be another sum of all of your displacement vectors. So for us, it's delta R1 plus delta R2. So just like any other vector addition, we're adding together the x's and adding together the y's. So we take these components from our two displacement vectors, delta R1 and delta R2, we put them in here. So that is going to give us 4.68 plus or minus 2.61. And then we're going to have negative 0.65 plus or minus 3.78. We end up giving us going to end up giving us this. So that is our total displacement. Now, just so we can draw it on the graph, I kind of want to know its direction. So remember, it's the inverse tangent of y over x. Theta is going to come out to be negative 65 degrees. which makes sense because with a positive X and a negative Y, what quadrant's that in? Fourth quadrant. So our negative 65 is going to be 65 degrees clockwise into the fourth quadrant. So if we were to take just the displacement vectors and put them on here, so we would have something like, there's one there. One here. We would get one here. With that being your negative 65 degrees. So displacement vectors can get a little tedious because you're going to have to do the same vector mathematics over and over and over again. But it's vector math that you've already been working with. You're either just adding vectors or subtracting vectors. So remember, the first thing you do is you find the components of all of your position vectors. You've been working on components. The next thing you do is you're going to do the vector subtraction to find your displacement vectors. Once you do that, you're going to do a vector addition to find your total displacement. Now, the good news about this is I'll probably give you like one of these on an assignment, but I don't think questions like this are important enough for exams or anything. We have other stuff we need to cover. Like I think it's more important that you learn how to analyze a kinetic system or something like that. But understanding displacement is important. Like again, understanding displacement versus distance. Like distance, remember distance is the total distance you travel. Displacement is the subtraction between your first and your final vector. You're going to find the same thing that, and this will become a little, depending on the textbook you read, it can be a little confusing, but like velocity and speed. Velocity is a vector, so it has a magnitude and a direction. A lot of textbooks will say speed is the magnitude of your velocity vector, but that's not completely true. Speed is going to be the average speed along your entire path of travel. So technically you could get a good approximation by taking the magnitude of your velocity vector, but we'll try to keep that separate so that we're not using terms equivocally. There's some vocabulary words for you. When you argue with people, do you speak equivocally or univocally? Trust me, you want to speak univocally, otherwise people can constantly move the goalposts on you and you never talk about anything. Okay, so that's just that's how you would end up analyzing the system of position vectors and their displacements. And then from there, we can start talking about some more physics. So we're going to go into velocity. Okay. So velocity and acceleration are both known as rates. Equation, why is it called a rate? It's a rate of change.
Distance over time.
Distance over time. And so you have to have that time, that temporal component, in order to have a rate. Now, so again, here you see your delta R, your displacement vector, your R final minus your R initial. You see your time, your T final minus T initial. Time is not going to be a vector. That's always going to be a scalar. If you were to guess distance over time, what do you think the normal, like the SI units for velocity are? Meters per second. So we're going to try to keep to that. Well, since we've been calling gravity an acceleration, what do you think the units of that are going to be?
Second squared.
Meters per second squared. So now the thing you notice is this delta R can also be broken into components. And this rate of change here is known as your average velocity. So your delta R is also going to have components. delta xi hat plus delta yj hat over delta t. So depending on what we're working with, your average velocity in the x direction, delta x over delta t, average velocity in the y direction, delta y over delta t. So a lot of times we can work with just these components, and you'll see that as we get into analyzing motion. Like for example, when you analyze the path of, like you throw something, you analyze the path it follows. You're going to break that down into x and y, and you're going to analyze each direction independently. So here we see average speed of a system. Can you see what I mean about it's actually the entire distance you travel, not just displacement. So the velocity you see is made off of a rate of change of displacement, whereas speed is a rate of change of distance. So speed technically covers the entire path that you travel. And you're just going to take little snippets of that travel, say like 0 to 5 seconds, 5 to 10 seconds, like, and you're going to average all those numbers together. That would be your average speed. So we're really going to try to keep speed and velocity separate so that we're not confusing the two terms. Okay. So here we go. We have a train that starts at 10 kilometers to the east of an origin point. So remember, another thing that's important is setting up your system so you can select an origin and get an X and Y axis that you're working with. It travels to a point 26 kilometers to the west of the origin point. You begin timing the train's velocity when it is at the 10 kilometer east position. And when you reach the 26 kilometer west position, 168 seconds has passed. So we're going to find the average velocity. Okay, so now this is something that you're going to want to really try to work on. When you're coming up with equations, you need to start asking yourself, what part of this can be zero? Okay. So that's the time that I'm looking at for my velocity. One of those can be zero. Which one is it?
The initial.
Initial time. Because I didn't do any timing before I hit that 10 kilometers east position. I just started there. So my watch or clock or whatever is at zero. So you say, well, I'm not going to need that. So that goes to zero. It's going to factor out of our solution. Okay, so let's kind of draw what this is going to look like. Okay, train only travels on a track, so I'm going to put an arrow there. That's positive X, and that's also east. West is over here. And if I put, well, let's put my origin right there. So then you have to ask yourself, and again, you have to put an origin in because it says at a certain point, because you're going from some east position to some west position. So you know the origin has to be between those two somewhere because you have to cross from one to the other. I honestly don't get how they chose to do that on the Earth, because somewhere in the Pacific Ocean, there's a line where you've gone so far west, you cross over to the east. Now, welcome to east and west on a sphere. But you know that the train starts at some position 10 kilometers to the east. It's going to end up 26 kilometers to the west. Okay, so then we say, what is the average velocity? Now, your generalized equation is the displacement vector. Do I need to go through all of that? Nope, I only need to work in the X direction. So, let's see. Let's think of this in terms of vectors so we understand why our signs come out the way they do. So, the average velocity gonna be delta x over delta t. So that's going to be x final. Let's see, I hat minus x initial I hat. And I'm just going to put over t because we remember t initial is 0. So the time that we're traveling is 168 seconds. Okay, so based off this being our system, what is the sign? What is the sign on x final? Negative, because your x final is going to go that way. That's the negative I hat direction. So we're going to have negative 26.0 kilometers minus, that's your positive I hat direction. So we're going to have a minus 10.0 kilometers. Okay. And that's going to be over 168 seconds. Okay, so what does our average velocity come out to be? Well, when you do this math, you're going to get about a negative 0.214 kilometers per second. And this negative, you want to make sure you include the direction. This just tells you, you know, which way your velocity is going. Now, the magnitude of this would just be 0.214 kilometers per second. And so some problems may ask for the magnitude, some may ask for, you know, the vector, but we do this analysis to make sure you know that the velocity is going towards the west. And then then you would want to change this. So kilometers per second is what in meters per second? 214. So, and then if you were to, again, if you were to do the magnitude, it'd be 214 meters per second. But I want to make sure we keep practicing with this direction, this positive and negative thing, because even though it's not as crucial in mechanics, now, I mean, here's a problem you could get wrong if you didn't take account of positive and negative. Because what if you took 26 minus 10? Okay, well, then you get the wrong answer. Because you'd end up with 16 divided by 168 instead of 36 divided by 168. So there are times when it comes in important. But remember, it's going to come in much more important next year when we're dealing with field forces. So, instantaneous velocity. Okay. Now, I'm going to show you this stuff in class. Since this is college physics, it's not going to show up on homeworks or exams. However, instantaneous velocity. So you notice that average velocity, we just cover a certain area over a certain time. We're just kind of looking for the average number in that, you know, in that, I guess these microphones are really bad, but you get the idea of the average. Instantaneous velocity is going to be, what is your velocity at a singular point? So you're traveling, you take a snapshot at a singular point, what's your velocity? Okay, well, to do that, you're going to have to start measuring that rate of change over smaller intervals until your interval is a singular point, which is what we call an infinitesimal. So you imagine your delta x and your delta t would be infinitely small because you want to capture that velocity at a single point in time at a single spot. And so if you think about a single spot, like if you're just not moving and you wanted to measure that with a delta x, it's going to be infinitely tiny. So the way you represent that, who's seen this kind of formulation before? No one's ever seen limits. Okay, so what this is is the mathematical limit as your delta t goes tends towards zero. Because again, a specific point in time, the change in time it's going to be zero. Because your t final, t initial would technically be the same. It would be an infinitely small difference. So as your delta t tends towards zero, your velocity, your delta r over delta t, your deltas also become infinitely small. So that ends up with this final expression here, dr dt. What do you think that is? Derivative. So that is good old calculus right there. Now, again, you're not going to have to do calculus on exams or homeworks, but I want to show you how this stuff comes from first principles. And there are going to be times in class where we use calculus because in an algebra-based book, sometimes they have to make asinine assumptions to get you to the right equation. And it's just like, do an integral. Like it's like area under a curve. Okay, so I'll show you how it works. You won't have to use it. You won't have to use it yourself. But let's kind of think about what this would look like. So we have an XY axis. Let's say that's the path that we're traveling, okay? So at the beginning, and let's go ahead and mark this as position versus time, okay? So you can imagine so we're going to have a displacement for the R1 versus R2 there. The average is going to be and of course, you have T initial T final. Okay, so we can do an average velocity for that. But what if we do it again? So we displacement for that one. So you can see your delta t is getting smaller and smaller and smaller. Now, what happens when delta t tends towards zero? So we're going to have almost a singular position vector at an infinitely small delta t. So that's the idea of a derivative. And so then what happens at this point is your instantaneous velocity you can imagine it going like this. And what kind of line is that? Tangent. Your instantaneous velocity is going to be a tangent to the curve you're traveling. So again, if you're thinking about it and you look at we'll be done here in a second, but let's try and look at a very kind of the same. You can never draw anything exactly the same twice. We still have our position versus time. You have the path that you're traveling. Your instantaneous velocity at any point on this path It's going to be a tangent to the curve at that singular point.
That's so.
Okay. So we're out of time for today, but that's the whole concept behind your instantaneous versus your average velocity. Now, the good news is for most of what you'll be doing this semester, you're going to be calculating averages, and a lot of it's going to be scalar numbers. So work it up in class in terms of vectors, so you get the idea of positive and negative direction. But as we go along solving problems, you'll see that it simplifies down quite a bit more. We just need to understand the underlying principles.
Since we're not gonna have lab tomorrow, are you gonna move the quiz and the test each back a week?
Oh, that's a good point. No, I'm still going to put the quiz up.
Okay,
Okay, so you'll see it show up on there, and you'll still have to do it, I don't know, by the end of the week.
okay.